Let's begin today with a review problem on power and home power. So it says calculate the resistance and the current, a 7.5 watt night light bulb plugged into a U.S. household outlet. So power is I squared R. And let's see what we know. We know the P and we know the V. We don't know the current nor the resistance. Let's see what we can do. V equals I, R. Let's solve it for R. So R is V over I. Now I've got something that I can substitute. I can substitute in for R, P equals IV. And I usually do the algebra, but I'll do it a little easier. We know the power here. Don't know the current. We do know the voltage, 120 volts. So I can divide both sides by 120. What you do to one side, you do to the other. I get 0.0625 amps. Now to get the resistance, I just go back and use Ohm's law. We already did part of this. V equals IR. So R is V over I, 120 over 0.0625 amps. And it's going to be a pretty high number. This must be a traditional light bulb, with a tungsten filament or something. And we get a resistance of about 1900, 1920 ohms. So there's a little review for you. And now we'll get to some new stuff for today, like household electricity. In the U.S., we use what's called a 110 line. It's actually 120 volts. Europe, it's 240, but they say a 220 line. And then in Japan, it's 100. Japan has its own setup. I guess they just developed their electrical system differently, and they never changed to the rest of the world. That's one of the reasons why you need special adapters if you go to Europe and you want to bring your hairdryer, your phone charger, your electric shaver, your laptop, any of your devices, you have to buy a special adapter. Now, surprisingly, you don't pay for power. You pay for energy. Power is how fast you use the energy. And the electric company actually doesn't care about that. For example, you could be at your house one day a month and run every appliance, run every washer, dryer, air conditioners, heaters, electric stoves. You could run everything in 1 month. Or you could use that same amount of energy slowly over a month. Well, but you've used the same amount of energy. That's what they charge you for. And they charge you for the kilowatt hour. Now, why not just regular watts? Kilowatts makes things a little bit easier to deal with. Now, a kilowatt hour actually corresponds, and I'm not going to go through the math right now, because we're going to do some math on the next slides, to about 3.6 million joules. So that's why they charge you for the kilowatt hour, because if they have millions of joules on your electrical bill every month, people don't understand those numbers. You can't send electrical bills with scientific notation. So let's say we have a 60-watt light bulb, maybe on a porch light, and we leave it on all night. So 12 hours a day for an entire month. That's 30, let's say it's 30 days. So let's see how many kilowatt hours we'll be charged for. So the power, I just went ahead and divided by 1,000. Nothing fancy here. 60 watts and 1,000 watts in a kilowatt. Kilowatt is 0.0600 kilowatts. Now, power is work over time, or energy over time. So energy is just power times time. Well, let's see how much time that would be. 12 hours a day times 30 days is 360 hours. So all I did was I substituted the power and the time, and we'll be charged for 21.6 kilowatt hours. That works out usually to a few dollars, because it's about 10 cents per kilowatt hour. Now let's run a dryer for 3 hours a day. So we do a lot of laundry every day, and the electric company charges 10.5 cents per kilowatt hour. The first thing we did was get the hours. 30 days times 3 hours a day, it's going to be a total of 90 hours for that month. Now the 1800 watts, I converted that over into kilowatts. I divided by 1,000. Remember, we said work is power times time. So here's our power, here's our time. That'll get us how many kilowatt hours we use. And we're getting charged 10.5 cents a day, or $0.105. So that's going to cost $17 to run that dryer for the month. A few more things on household electricity, and then we'll wrap it up. Now, circuit breakers are in your house and in my house. We all have a circuit box down in the basement. These prevent overloading. You don't want too much current per wire. If you're trying to draw too much current through a wire, it could overheat, it could melt, you could have a fire, it could be a dangerous situation. So we prevent that. Older homes had what were called fuses, and we still use fuses usually in cars. And what fuses, and I even have some devices in the back of the room that still have some fuses in them. Fuses have a little metal ribbon, and it's inside something that you screw into the fuse. If things, and they can look either way, they both, some of them look like this, like in a car. If you've ever changed a fuse in a car, it looks like that. It looks like a little cylinder. Or some of them you have to screw in the old fuse boxes. And then if too much current goes through, this metal strip melts. And then you have to throw it away. But because it melts, it breaks the circuit, and you're going to help your house. You're not going to hurt your house. More modern ones look like this. They're a box, and they have a switch on the outside of them. And they have what's called a bimetallic strip. So it's two types of metals. Not all metals expand at the same rate. Some expand a lot when you heat them, and some don't at all, or very little. So what happens here is when this gets too hot, this kind of gold or bronze colored strip expands more than the other one. And you see how now we have a current, and it slips over here. So the whole thing bends and slips over here and leaves a little air gap. So now the circuit is open, and that's what you want. You want to cut off electricity to that part of the house so you don't end up with a fire. And for the most part, modern circuit breakers use this, and you just go down the basement or into your circuit box and you flip it. Here's something that could really help you when you're jump starting a car. You always want the positive part of one battery, and then you have your jumper cables, to the positive part of the other. Try and draw a quick little battery in here. Something like that. It's not too good, but that's okay. Something like that. Then negative to negative. And usually if you start to hook them up the wrong way, you'll get a spark, and you'll know. Be very careful when you're doing that. That's super important, because if you don't do that, your battery could explode. So it's always positive to positive, negative to negative. And just a real quick slide or two, because we're not going to do a lot with AC power, is the difference. DC power usually comes from a battery. Now I'm showing the electron current, but the conventional current just goes in the opposite direction. In DC power, the current flows constantly, and the conventional current would go the other way. Just to remind you, because it's important to know. But they just flow and flow and flow, and they flow in only one direction until the battery runs out. So it would be like if you went to a track and you want to run or walk, and you only went in one direction. Usually that's what you do. You just go, and you go whatever direction everybody's going, and you run or jog or walk, and you keep going around that direction, and you do your laps. AC is different. In AC, they switch. So in AC, the electrons go one way, and then they switch and go in the opposite direction. And they do this 60 times a second, or 120 times a second, for a total of 60 hertz, or 60 cycles per second. This is your house current. So the analogy I use is, now you go to the track, and you don't want to get bored going in the same direction. So you run one lap one way, turn around, and go one lap the other way. And you do that every lap. You switch it up. You clockwise and then counterclockwise, clockwise and then counterclockwise. And that's house current. You might say, well, why doesn't house current use DC? It turns out that AC current is much, much better. There's a lot less loss of energy when we ship it over power lines. So think how big the United States is. We have to get a lot of electricity to a lot of homes, some very, very far away. AC, you have less power loss doing that. And the idea of using AC current for this was Nikola Tesla, whose name you may know. Thomas Edison wanted to use DC current, and some of you may even know, there was kind of a competition, but Tesla really won because DC worked fine for where Thomas Edison was, near New York City. It wouldn't have worked fine for power lines, to Pennsylvania and Nebraska and California and places where things are very far apart.